In this lesson, we're going to look at the crossover method, but this time we're going to examine compounds where we have multivalent metals involved. Just a reminder that the crossover method is the method used to write formulas of ionic compounds from the name. So we write the formulas down, then we take the magnitude of the charges, so the number associated with the charge, and we cross them down or swap them. And then we simplify to get the smallest ratio. The goal of this, of course, is to lead us to building a formula that has no net charge. So far, our experience has involved elements where we could identify the charges of the ions based on the position on the periodic table. So a reminder that group 1 had a 1+ charge, group 2 has a 2+ charge, group 13 has a 3+ charge, then we have 3-, 2-, and 1- for our most typical elements that we'll be working with. Now, we've just been skipping over the transition metals and we haven't used any of the elements that are larger and lower on the periodic table. And it's because these metals are often what we refer to as multivalent, which means they have more than one possible charge where they can be found to be stable. In our first example, we're going to be looking at iron, for example. Iron is stable as Fe2+ or as Fe3+. Now, at this stage in our chemistry journey, we don't have the atomic structure knowledge to be able to justify or to explain at the atomic level why these two possible charges exist. At this stage, you're just going to be working with a large number of compounds and you'll be given the information so that you know what the charge is on the elements that you're working with. Now, one thing to note though at this stage is that zinc and silver are special cases that we need to remember. They both are not multivalent, even though they are transition metals. Zinc will always be found in a 2+ charge and silver as a 1+. A way to remember this, and it's just a pattern in the periodic table, it has nothing to do with the atomic structure, but if you remember that aluminum is 3+ based on your pattern in the periodic table, then if you go diagonally down, we have zinc being 2 and silver being 1. So it's a 3-2-1 pattern. For the other elements, you'll see that you'll be given the charge. Now let's come back to our Fe2+ and 3+ and see why the fact that we have these two possible charges poses a problem in our nomenclature or our naming system. With Fe2+, if I were to build a formula with chlorine, I would find that I have FeCl2. And with Fe3+, if I build a formula with chlorine, I would find that I have FeCl3. Following the pattern of naming that we've seen so far, where we name the metal and then the anion, both of these would have the same name of iron chloride. This is a bit of a problem. So how do we overcome this? We need to change the rules so that we can identify the charge on the iron within that compound. So you can see here what I've done is I've updated the name and it's iron 2 chloride and iron 3 chloride. So what this is showing you is that when you see Roman numerals after the name of the metal, that is signifying to you what the charge is on the metal ion. And remember that the metal is always positive in our compound, so it's not a mystery to me that this is 2+, okay? Because I know that the metal will always be positive. So when I want to write my ions, I'll be able to do that. And we'll look at some examples in a minute. In terms of our Roman numerals, it's new for some people, but we have 1, 2, 3, 4. Those are basically the ones that you will need to know. So let's look at some examples. If we want to look at the formula for lead 2 chloride, to do the crossover method, I need to write my ions down. and then I cross over. In this case, the lead is a multivalent metal, so I can't use its location on the periodic table to figure out its charge, but the 2 indicates to me that the charge is 2+. Chloride, based on its position on the periodic table, has a 1- charge, and then I can cross over, so the 2 and the 1 cross down, and I am left with PbCl2. My positive and negative charge are going to be balanced within this compound. If we want to look at the formula for copper 2 oxide, once again, when I see the Roman numerals, that is indicating to me what the charge is on the metal ion. So in this case, I have Cu2+. I can determine the charge on the oxide or the oxygen ion based on its position on the periodic table. It has a 2- charge. When I cross over, I get a 2-to-2 ratio of each of the ions. Essentially, I need one of each of them in order to get a net zero charge. So when I simplify the ratio, I'm left with CuO as the formula for copper 2 oxide.